We're going to look at orbital motion. This is going to be a connection between the circular motion things we've already learned, as well as the things we've learned about gravitational force and acceleration on a large scale. We'll finish up by talking about Kepler's laws that expand this from just a circular orbit to any elliptical orbit, of course, which a circle is a special case of. We know this now, but if you imagine when Newton was saying, okay, we've got this force of gravity. That's what's pulling the Earth in orbit around the moon in orbit around the Earth. A lot of the skeptics said, well, why doesn't it just crash to Earth, right? He was sort of comparing the apple and the moon to each other, the classic Newton's apple, which I'm sure that story is a bit apocryphal, but certainly things fall, right? We drop them there in free fall. And to say that the same force that causes that to happen causes the moon to be in orbit is nice because it keeps everything consistent, but excuse me, it can cause confusion. And so what Newton said is, well, and what we know to be the case is that the moon is falling, right? It goes in an orbit. It tries to go tangent, but the force of gravity pulls it into a circle. And the acceleration due to gravity, which we know is about 0.0027 meters per second squared, which we can get because we knew the orbital radius of the moon relative to the orbital radius of the Earth, a little factor analysis. And so we get this distance that it falls down away from a straight line path over time. And so the way Newton explained this was by doing what we would consider sort of a thought experiment called Newton's mountain. When you're standing and you throw a projectile, horizontal projectile, it goes and it hits the ground. And if you double the speed, it travels twice the distance horizontally because it takes the same amount of time to fall. But, and this is a video that I highly recommend going to look at, certainly the middle section of it, where it talks about Newton's mountain, a nice animation. I won't show it here, but you can go look at it. But if you imagine standing on the top of a huge mountain above the atmosphere, but still connected to the Earth, and you throw the ball, right? The Earth curves away beneath it. So as you throw it, doubling the speed doesn't double the distance. It more than doubles it because the Earth is falling away underneath it. And if you throw it at just the right speed, fast enough, it will go around and come back and form a perfect circle around the Earth, right? The ball is in continuous free fall with acceleration due to gravity being the centripetal acceleration. And there is a particular orbital speed where that centripetal acceleration would work and we get a nice circular orbit. So here's kind of the way this works. You have, too slow, any speed less than that perfect circular orbital speed, it will go and hit the Earth. Then there's a point at which you get sort of an elliptical orbit. This is very hard to do that second one when you're standing literally on top of the Earth. But then there's a perfect circle. And then if you go even faster, it gets a more eccentric ellipse. And if you throw it fast enough, you can actually achieve what we call escape velocity, which is the speed so that it will never come back to Earth, will never orbit back around. We'll talk more about that when we get to energy and momentum conservation. So why are space station astronauts orbiting the Earth weightless? If you remember back to our previous video, we said that at the International Space Station, little g was about 8.7 meters per second squared. Well, they're in free fall, right? No normal force. So just like in the elevator where the cable is cut, just like jumping through the center of the Earth in that, tunnel problem or example, you feel weightless because you don't experience anything pushing against gravity. Everything, the space station, the astronauts, everything around them is in free fall. It's experiencing that acceleration due to gravity. So when it comes to orbital circular motion, we have this fundamental idea that the centripetal force is provided by the force of gravity. And if that is true, then we have the mass times the centripetal acceleration is equal to mv squared over r, but that's equal to fg, which is also gmm over r squared, which is also mg. And then of course you know that v is 2 pi r over the period. So if you combine all this stuff about circular motion and gravitation together, you can actually do some really interesting things. For example, we've got Supergirl standing on Newton's mountain. How fast does she need to throw a baseball to put it in orbit? So Newton's mountain is sort of this little bit of a trick in that you're at the orbital radius is the radius of the Earth. So that's simple. So little g is just 9.8 meters per second squared, but you're technically above the atmosphere. So we've got mv squared over r equals gmm over r squared. The mass of the ball cancels out. V is equal to the square root of gm over r. So this works for any particular orbital radius around a planet or object of mass capital M in this universe where big G is our constant, right? And near the surface of the Earth, for like this example, you get 7,900 meters per second, which is pretty nice. Or we could say, when you're near the surface of the Earth, I already know that its little g is 9.8, and we get the square root of rg. An even simpler equation, if you know what the acceleration due to gravity or gravitational field strength is at that point, we get the same answer. So how long does it take the ball to get all the way around? This is the period of the orbital motion question. So we can start with the definition of circular motion speed, which is 2 pi r over the period, right? We know the orbital speed. We know the radius is the radius of the Earth here. We can find out that it's 84 minutes, which, if you recall, is the answer that I gave you for saying that was how long it took to jump back and forth down through the tunnel in the Earth in our previous video. So for circular orbits, you're going to combine which of these pieces gives you information that is useful, right? Maybe you know about the centripetal acceleration. Maybe you know about the mass of the Earth. Maybe you already know little g. Maybe you're looking for the period. And you combine those together to find useful things, remembering that little g is only something we've memorized and known near the surface of the Earth. Otherwise, we'd have to either calculate or use one of the other formulas. Right? So here's another interesting example. Now, this one is a binary star system. Now, they're orbiting in a circle as shown. That x represents the center of mass of the system. We want to find the orbital velocity here. Well, they're both being pulled toward the center, right? So the force is gmm over r squared. And then we have mv squared over r for the circular motion. But there's something wrong. I've used the same r value for both the radius of the orbit and the distance between these two masses, but they're not actually the same here, right? The r value that I wrote there is the distance between the masses, gmm over r squared. But the distance between the center of the orbit or the radius of the circle they're traveling in is actually half that. So we need to replace this with mv squared over r over 2 equals gmm over r squared. Now, one of the masses cancels out, and we end up with v equals the square root of gm over 2r, basically giving us a slightly different answer than we would get for just an object orbiting a central mass. In this case, if they have unequal masses, then it turns out they'll still orbit the center of mass, but they would not be orbiting at the same radius. So that's a slightly more complicated answer. All right, last thing to talk about here with motion is Kepler's 3 laws of planetary motion. They are as follows: the law of ellipses, the law of equal areas, we'll talk about that later with angular momentum, and the law of periods. The law of ellipses is pretty simple. It just means that planetary motion and orbital motion in space is elliptical, where the central mass is actually at one focus of the ellipse. And the third law talks about some interesting relationships between mean distance from the sun, r, which would be the orbital radius if it were a circle, and the period in Earth years. And so Kepler did a lot of observing of planetary motion. And if you look at all these numbers, they probably don't mean anything to you. They don't mean anything to me just off the top of my head. But Kepler found that if you did something like square the period and divide it by the mean distance from the sun, or orbital radius cubed, you got a constant. Now, I don't know exactly why he thought that this would be a good thing to do. Maybe he was just squaring and cubing and, raising to various powers and looking for patterns, which is reasonable to do when you've collected an observational data set like this. You don't necessarily have a theory of how it works. You just need to look for patterns. And if you do that, what you notice is these are all essentially the same number, right? About 3.3. And that led to a really interesting result. He figured out that there was this particular ratio that was true for everything orbiting the same thing. So for every planet orbiting the sun, for every satellite orbiting the Earth, for everything in the galaxy orbiting around the supermassive black hole that we think is at the center of the galaxy, and so on, right? This ratio is true. Now, Newton was the one who kind of put together all of the details of the why of this using Newton's law of universal gravitation. So here's how it goes. If you start with the basic idea that for anything orbiting the sun, we've got g times the mass of the sun times the mass of the planet divided by r squared, which is equals mv squared over r. We cancel those pieces out. We end up with substituting in for v with 2 pi r over the period. We end up with period squared over radius cubed. Orbital radius cubed is 4 pi squared over gm, a constant for our solar system, right? Where mass is the mass of the sun, or for any solar system, or for all of the things orbiting the Earth, if that is the mass of the Earth. And that constant ends up being really important. Now, the nice thing is, from an astronomical perspective, from a cosmological perspective, if you're observing a distant, say, extrasolar planet, you can figure out the period by repeated observations. We can usually figure out something about the orbital radius. And then the only unknown there is the mass of the star it's orbiting, which is actually something you can find using this. There are two ways to apply Kepler's law. One is to use this formula, sort of the Newton and Kepler together formula. This requires SI units because it's got big G, which is in a particular set of units, kilograms, meters squared, kilograms squared. But if you have two objects orbiting the same central mass, like Mars and Jupiter, all you need to know is the period and the radius of one and the period of the other, and you can get the radius, or vice versa. And it doesn't even matter what units you use, right? You could use years, you can use days, you could use kilometers, you could use AUs, astronomical units, which, since we humans invented them, is just the distance from the Earth to the sun on average. And you can use any consistent units. It doesn't matter what they are. They don't have to be SI units. So you don't have to be in seconds, which can be an unwieldy unit for time when you're talking about period of the Earth. A year is a much simpler number to use than however many seconds a year is. So very important that there's these kind of two different methods. For number one, you should be able to get there using what we know about circular motion and gravitation. For number two, it's just a ratio that's worth remembering. So here's an example. If a planet in our solar system has an orbital radius of twice Earth's orbital radius, right? Some new planet suddenly appears there. What is its period? Well, we can use what we know about Earth and its period and radius. And our two objects are 1 and 2, right? Period of 1 is period of 2 times 3/2 of the ratio of their orbital radii. We can plug those in. The radius of the Earth's orbit cancels out, and we get a 2.83 Earth years. So this is really the power of this, that it gives you a relatively simple number pretty quickly without a bunch of exponents and scientific notations. Another example is, what about a geosynchronous satellite orbits over one spot on the Earth? What is its altitude? Well, there's some interesting things going in here hidden in the words. Geosynchronous means it's over the same spot on the Earth all the time, which means it must go around the Earth once every day because that's how fast the Earth turns. And then the altitude is not the distance from the center of the Earth. That's not r. It's actually the distance above the Earth's surface. So we know that it stays directly overhead, right? And we can use our second object as, say, the moon, because we know about the moon. It's also orbiting. So we can find its orbital radius by using that relationship. 1 day to go around for the geosynchronous orbit, 27.3 days for the moon. And then we have that factor. We have 60 Earth radii for the moon. We find out that it's 6.6 Earth radii for this geosynchronous satellite. And if it is a distance from the center of the Earth of 6.6 Earth radii, that means it is 5.6 Earth radii, one less, above the surface of the Earth. So Kepler's third law then can also apply to elliptical orbits. R is just no longer the orbital radius. It's the semi-major axis of the ellipse. And when we're talking about that, it's the distance from the center of the ellipse along the long axis out to the point on the ellipse. So that's it. That's what we've got. for orbital motion. Hopefully that makes a little bit of sense. We'll talk more about it, and we'll do some practice problems in class.